Okay, so on tap for today is, like I said, we're going to do study assignment A, which is about sig figs, conversions, all those type of things. A reminder that you can find all the study assignments in your lab manual near the back. So after sort of all the sort of physical experiments, you can find it over there in sort of the back. There's like study assignment A through, I want to say G or something like that. Again, they're pretty much like worksheets and stuff like that. And you can basically work through them. You do need to make sure that you show all the work for anything, obviously, that has work associated with it. Obviously, for this particular one, it's all about significant figures and stuff like that. So that's obviously important in terms of your answers and stuff to make sure everything's in the proper number of significant figures and everything like that. But before I just sort of release you to kind of do all that kind of stuff, I did want to kind of go over significant figures, conversions, all that kind of stuff there. Again, in our book, it's more of a sort of the pre-chapter, I think, rather than an official chapter. You are responsible for knowing these things like significant figures, conversions, density, and those type of things, temperature conversions. So there might be some questions on that on exam 2 as to where it might show up. So you are responsible for this material. And again, if after our talk here and stuff, you still need a little bit more information about it, again, I believe in the introductory sort of chapter to the book is where you could kind of find that information. But I am going to go and talk about some of these things. And again, just to make sure hopefully everybody is on the same page. So let me do that there. Okay, so in that sort of opening chapter, if you will, and stuff, and again, deals with it deals with significant figures and all that kind of stuff. So we'll start with that. As you may be familiar with, really, whenever you take a measurement, for example, there's always some degree of uncertainty in a measurement. The degree of uncertainty in a measurement depends on basically the equipment that you're using. So for example, if we had a ruler, very badly drawn ruler there, we'll go with 1. We'll go with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 markings between 1 and 2. We'll call these centimeters, for example. So we have 10 markings between 1 and 2 centimeters. So whenever you take a measurement, you want to figure out what does each marking mean. So since there's 10, that means each marking is basically 0.1 of a centimeter. And that would make that 1.1, 1.2, and so forth all the way across. So if we were taking a measurement of an arrow or something like that, such as this, when we would take this measurement, there should be certain numbers that pretty much everybody agrees upon. It's at least 1.1, 1.2, 3, 4, let's track 3, 4, 5, 6, 7. No matter who takes a look at it, everybody should agree it's at least 1.7. The problem, though, is it's not exactly 1.7, which is here. It's not exactly 1.8, which is there. It is somewhere perhaps between. I may look at it and go, I think it's perfectly dead center. I'm going to record 1.75 centimeters. Somebody else may look at it and go, I think it's closer to the 8. Maybe it's like 1.77. Somebody may say, no, I think it's closer to the other way, 1.74, 1.73. So that's where the uncertainty comes in a measurement. And you should always look at the equipment, the scale to take a proper reading. When we do record stuff, though, in terms of a measurement, we should always record all the certain numbers plus that first uncertain number. And basically that, when you do that, is basically what was referred to as significant figures. So significant figures is really in a measurement where you record all the certain numbers plus the uncertain number. Uncertainty is here. What that basically means is this could be maybe like 1.76, maybe as low as like 1.74, plus or minus that last digit. Just like when we take a reading, that's say 10. That's 20 milliliters. And when we read a liquid, badly drawn here, when we read a liquid in a glass container, we usually see the bending or the curvature of the liquid, and that is what is known as the meniscus, right? We always read from the bottom of the meniscus. So if we look at this, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 markings between 10 milliliters and 20 milliliters. That means each of the smallest markings is 1 milliliter. And that means this is like 11, 12, right? 13, 14, 15, 16, and so forth. So if I were to look at it, that's definitely 15. Everybody would agree. Again, if we're recording from the bottom there, it's definitely not exactly at 15, not exactly at 16. Again, there's some type of estimate that has to be made. And I would record something maybe like 15.5 milliliters. That is all the certain numbers plus that first uncertain number here. And again, those are all the significant figures. So this guy would have 3 significant figures. This guy over here, the first one we did, would also have 3 significant figures. So really important when you take measurements that you record things to the proper number of digits and the right number of significant figures. And it really does matter. So for example, if we looked at our first one, and let's just say our thing stopped like dead on here, like right on the 1.7. If you record 1.7 centimeters, or you record 1.70 centimeters, there is actually a difference in each of these measurements that you recorded. When we look at this guy, this would imply that there are 2 significant figures, with the 1 being the certain number, the 7 being the uncertain number. And what that means is that this measurement, if you recorded 1.7 thinking the 0 is not that important, what you are saying is this measurement is like 1.7, but it could be 1.8 or it could be 1.6. And obviously here's 1.6 over here. It is nowhere near it. And here's 1.8. It is actually nowhere near it. So this would be a really crappy measurement that you just took because you decided to lop off that 0. So this would not be the right way to record it. This actually would still be the right way to record it because on this piece of equipment, we have the ability to take it to that second decimal point. These guys would be our certain number. This 0 here would be our uncertain number. This guy would have 3 significant figures in this case. And what this measurement tells us is, I think it's 1.70, but it might be 1.71 or it might be 1.69, which, would be like right here or here, which is pretty realistic based on what we see here in the picture. So sometimes people think, well, it's dead on the number, I'll just get rid of the extra 0. And you should never do that because pretty much you're making that measurement pretty bad when you do so. And again, if you have the ability on the scale to go to one more place, you should keep it and you should put it as a 0 if necessary. In most cases, when you're taking a measurement, you usually could go one more place to the right of the smallest measurement. Not 100% of the time, but most of the time, you can go one more place to the right. So for example, here, smallest measurement was the first decimal place. We're able to go to the second decimal place. Smallest marking on this scale was 1. We're able to go to one more decimal place, which is the first decimal place in this case. So typically speaking, in most cases, when you take a measurement, you could go one more place to the right of the smallest marking. Any questions on actual measurement taking with significant figures? Okay, then let's talk actually about significant figures and how to identify them. So all non-zero numbers are significant, which means if you have 2, 3, 4, they're all zero, all non-zeros. Start counting left to right. That would have 3 significant figures. Zeros is the thing that gives people the hardest time. There are 3 different types of zeros. There are leading zeros. Those are not significant. So 0.000111. None of these zeros are significant until we get to here. That is where we start counting. And this guy would have 3 significant figures in this particular case. The next type of zero is sort of a zero that's trapped between 2 non-zero numbers. And those guys are significant. So like 2004, start counting here, significant. These zeros are trapped, they're significant. Guy at the end, significant. This guy would have 4 significant figures in this particular case. And lastly, we have zeros that are at the end of the number. And they may be significant or not. And what determines if they're significant or not is there a decimal place in the number? So for example, if I write 100 like that, no decimal written, it has only 1 significant figure, and it would be this guy right there. If I write 100 with a decimal point at the end, this guy would now have 3 significant figures as a decimal turns them all together. If I had 0.00500, these would not be significant. This is significant, 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 because there's a decimal point right there I circled. And that would give this guy 3 significant figures. Any questions on how to figure out if a number is significant or not? Now, more importantly as well is when we do calculations involving significant figures, we want to make sure that we give the answer to the proper number of significant figures. We'll get to scientific notation just this second, actually. As soon as we finish talking about this, we'll hit scientific notation. When we do calculations that involve significant figures, there's really kind of 2 types of calculations that we do. We do multiplying and dividing. So when we multiply and divide, the answer should have the same number of significant figures as the number with the least amount of sig figs. So if I took 325 and I times it by 0.10, this number here has 3 significant figures. This number here has 2 significant figures, these 2. That means that my answer should end up at 2 significant figures. So again, you want to keep track of what you're doing, multiplying, dividing. Significant figures is what you're looking at. If you add or subtract, you are looking at decimal places, and it is the number with the least number of decimal places. So if I take 3.25 and I add 1.2 to it, this is 544. Adding here, this guy has 2 decimal places. This guy has 1 decimal place. We would go to here to actually 1 decimal place. That's a 5, which means we're going to round up. Normal rules apply. 5 and above, you round up. 4 and below, there, we just drop the numbers. We end up with 4.5, which is 1 decimal place, but 2 significant figures. So adding and subtracting, we're not looking at significant figures, but we're looking at decimal places. Multiplying, dividing, we are looking at significant figures. Any question on those too? If you are doing multiple steps in math, you want to kind of keep track. So if we were multiplying 325 times 1.220 times 3.2, and then we're going to divide it by 1, 2, 3, 4. Very creative in the numbers, I know. So we're multiplying the top here. We would look at sig figs. So that would be 3 sig figs there. This guy would have 4 sig figs, the middle guy. Last guy would have 2 sig figs, which means technically speaking, when I do the top calculation, I should end up with 2 significant figures because that's the least. I then would be taking that 2 significant figures and dividing it by the bottom number, which is 4 significant figures. That means my answer should end up at 2 significant figures. So if you're doing a combination of adding, subtracting, multiplying, dividing, you do want to keep track of your significant figures as you're doing those calculations. A good rule of thumb also is maybe not to round too much until the very end. So if you do a lot of rounding along the way, you will end up with an answer probably very different than the real answer. So try not to round too much. But if you are doing multiple steps, you do want to kind of keep track of everything in terms of, significant figures and what you should sort of take everything to. Any questions on that there? Since we spoke a little bit about rounding, let's talk a little bit about rounding and not doing extreme rounding. So rounding kind of normal. Again, 5 and above, we go up. For less than that, we go down, and not really down, we just drop off the numbers. But if we had something like 13,333, and I wanted to round to 2 significant figures, that would take me to here. So I could round to 13. I could go to 13,000. Which one would be right here? Hopefully you know, but just to make sure. This number here has 2 significant figures. So it is good, but it's really not good because if I owed you $13,333 and I said, hey, I'll give you 2 significant figures, here's $13. I'm probably not going to make it out, I imagine, too well there. Although it is 2 significant figures, there is a very big difference in the meaning of the number between $13,333 and $13. So although it's the right number of significant figures, when we round, we never want to change the actual meaning of the number. Now, if I go over here, $13,000, no decimal point written anywhere. This would be the 2 significant figures here, which is good. And perhaps there is a pretty close relationship between $13,333 and $13,000. Perhaps you give me the nice chemistry teacher discount of $333, and maybe I make it out okay in that situation because of that. So sometimes, and it's very common, that people will really try to hit the right number of significant figures and do what I call extreme rounding so much that all they focus in on is significant figures, but not the actual meaning. So again, you never want to change the meaning of a number by rounding or doing any of that extreme rounding. Any questions on that there? All right, so let's actually talk about scientific notation, as was an earlier question. So scientific notation has the general form of n times 10 to the n. This is a number between 1 and 10. So not 10, 20, 100, not below 1. It needs to be a number between 1 and 10. This is either a positive or negative number. depending on which way you move the decimal point. So if I had 425, 325, we would assume the decimal points here are 1, 2, 3, 4, and 5 places to the left. Gives me 4.25325 times 10 to the 5th. If I have a smaller number, 125, I would go 1 place here, 2 places here, 3 places here, 4 places here. Gives me a number of 1.25, which is a number between 1 and 10, times 10 to the minus, what did I count there? 1, 2, 3, 4. So important to know how to write things in scientific notation. Also important to know, how to do it properly. So again, here we would go 1, 2, 3, and 4 places. This would be 4.2 times 10 to the 4, I think is what I counted there. Now, you may be wondering, why maybe I got rid of some numbers here, why I kept all the numbers here. And that is because when you write a number in scientific notation, all of the numbers that come before the times 10 part are significant. Which means when you turn a number into scientific notation, or you go scientific notation back to the number, you should never lose significant figures. So this original number had 1, 2, 3, 4, 5, 6 significant figures. When I write in scientific notation, it has 1, 2, 3, 4, 5, 6 significant figures. This number here had 1, 2, 3 significant figures. When I wrote in scientific notation, 1, 2, 3. This number had only 1 and 2 significant figures. These zeros are not significant because there's no decimal point written in the number, which is why when I turned it into scientific notation, I went with 2 significant figures. The nice thing about scientific notation is you could actually control how many significant figures you are given in an answer by writing a number in scientific notation. And sometimes the only way you could get a number to proper scientific notation, to the proper number of significant figures, is to write it in scientific notation. Question on that? Now, I won't go into it too much here because I think we went into it pretty significantly earlier on when we were doing the calculations. A reminder that when you put numbers in your calculator in scientific notation, again, make sure that you are using your exponent button. Again, most calculators have an exponent button like one of these. Remember, these are the ones that when you push it, like 1.5 times 10 to the 5th, you would go 1.5. You hit your exponent button, no multiplication, nothing else, just the exponent button. That 1.5 will pop up that E. That E represents the times 10 part of the number, which is why you don't hit the multiplication or anything like that. You just hit 5 and it makes like a 5. You may also, again, as we talked about, have that newer calculator, which may be a button like this, not the button over the log, but an actual button like that. The only difference is you need to put parentheses around your number when you do that. So you need to do that type of deal. You then need to hit 5. By the way, you then need to hit that button right there on the right. It will bring down your parentheses and you close it. But most importantly, probably for us as well, again, is to being able to properly type these things into your calculator. Hopefully you have that worked out since we did a lot of exponent calculations there in the first couple of chapters. But a reminder that if you're finding yourself with answers that look pretty close to the right answer, but just off, it is probably the way you're punching it into your calculator. Any questions on the scientific notation there? Okay. Let's see. We got that. We got that. Then let's talk a little bit about some temperature conversions, which is something we hopefully should know. In chemistry, right, we deal with 3 different temperature scales. There's degrees Celsius, there's degrees Fahrenheit, and there is capital K, which is Kelvin. First major difference is it is not degrees Kelvin, it is just Kelvin. And we convert between these. So if you want the temperature in Fahrenheit, you take 1.8 times the temperature in Celsius plus a 32. If you want the temperature in Celsius, you take the temperature in Fahrenheit and you minus 32 and divide it by 1.8. That 1.8 number is the same number maybe you learned when you're younger as 9/5, the fraction, same deal. So those are two common conversions. Well, not really common. We don't use them all that much here in chemistry, Fahrenheit, and we do use Celsius. But the one we use the most is going from Celsius to Kelvin. So the temperature in Kelvin is the temperature in Celsius plus 273. And that is definitely a conversion we use a lot in chemistry. The opposite of that is if you want Celsius and you have Kelvin, temperature in Kelvin, minus 273 will get you there. The correct number is 273.15, but very few people use the 0.15 version of it. And most people just use 273. If you like the 0.15, you could use it, but most of the time it kind of gets rounded off anyways. So a lot of times people will not use it, but you can use it if you want. So again, most of the time, this is probably your temperature conversion you're going to do. So you definitely need to know that. You should know all of these as well, but probably not going to see too much of these guys, I would think. More so, we'll see these, and probably out of all four of these, this guy up on top is the one, obviously, that you would use a lot. Any questions on that there? All right. Another important thing is conversions and dimensional analysis. So perhaps you might remember dimensional analysis. That's a fancy word for conversion problems, basically. So dimensional analysis is a way we do conversions where we really do see kind of all the units cancel. So for example, if we have an equality, so for example, 1 inch is 2.54 centimeters. This is what is referred to as an equality. It basically is two measurements on different scales, but they represent the same amount of something. Just like if I had 100 pennies, that is the same as $1. They both represent the same amount of money. You could go through a drive-through and pay in pennies, or you could pay in dollars. I imagine if you pay in pennies, they might put your sign up and not welcome you through the drive-through every day, but you technically could. It is money, and it does represent, the same amount. From any equality, we really could write two conversion factors. And when we do conversion factors, they're basically just fractions. So we could say, for example, in 1 inch, there is 2.54 centimeters. Or in 2.54 centimeters, there is 1 inch. Same thing over here. We could say 100 pennies is $1. Or $1 is 100 pennies. We typically would not use both conversion factors in a problem. We would just use one or the other for each of these guys. So let's just say, for example, we had, we had 42.5 inches, and we want to know how many centimeters that is. When we do sort of problems in chemistry, we do dimensional analysis. And what dimensional analysis is basically showing the calculation with the conversion factors and the units and everything canceling correctly. So we would take 4.25 inches, which is what we're starting with. Now, although it is not written as a fraction, it is kind of like a fraction. The inches are on top. And when we do dimensional analysis in units to cancel, we always go opposite in terms of the units so that they cancel. That means we would then multiply it by this conversion factor, where we have 2.54 centimeters up on top, 1 inch on the bottom. Basically, what we're doing is we're multiplying what's on top, and we're going to come back and divide by what's on the bottom, basically. So when we do this, we're essentially dividing inches on top and inches on the bottom. That equals 1. Same idea. If you divided 2 by 2, it equals 1. If you divide the inches on the top and inches on the bottom, they cancel. That ends up giving us 4.25 times 2.54. It gives us an error if you punched the wrong button in. Try that again. 4.25 times 2.54. 10.795 here. The units that are left are the guys that are on top, as these guys will cancel. And we have centimeters. In terms of significant figures, for the most part, any type of equality is considered what is referred to as an exact number. What's an exact number? An exact number is something that is really not measured. It's either a definition, like what we got here, or it is something that it was counted. So if I had like 5 apples on the desk, I wouldn't find some scientific way to figure out how many apples I have. I would simply go over and count. Hey, I got 5 apples. So exact numbers actually can have as multitude of significant figures. So that means that really the only real number we have to worry about is the original number here, which has 3 significant figures, which means my answer should actually have 3 significant figures. That means we should end up with 10.8 centimeters in this particular case. You do need to show your work this way. You do need to show your work this way in chemistry using dimensional analysis, showing the units canceling. You could do it in steps. You could do multiple steps, but you do need to show that when you do any type of calculation, really. Any questions on that there? Now, what happens, for example, if I had 32.5 inches cubed, and I wanted to convert that into centimeters cubed? When I do a conversion like this is also very commonly screwed up. We can use our same equality that 1 inch is 2.54 centimeters. We could approach it the same way, start with our 32.5 inches cubed. We would want the inches on the bottom so that they cancel. 1 inch is 2.54 centimeters. Now, if I do this, only 1 inch is going to cancel. I'm actually going to be left with inches squared, which is a very common mistake that people do. So I don't need to do this conversion once. I actually then need to do it another time. That inch will cancel the second inches cubed. And I need to do it one more time here. To completely cancel it. And that means when I do this, I'm taking 32.5 times 2.54 times 2.54 and times 2.54. And that gives me something like 532.57958 units left. Centimeters times centimeters times centimeters gives me cubic centimeters. These are all definitions, which means they're exact numbers, so we don't have to worry about sig figs. Usually in conversion problems, you default back here to our sig figs here. That's 3, which takes us to here. Should end up at 533 cubic centimeters. I can't tell you how often people do this conversion once, or better yet, they have the right idea and they set it up like so. But they actually don't cube it. They actually just end up doing it once. So sometimes it's best to maybe write it all out so you don't forget to actually do it. Again, I can't tell you how many times I've seen it set up like that, which is technically right. But I've also seen many, many times people actually not do the right part of the math there and end up with the wrong thing. Question on dimensional analysis, conversions, and stuff like that. let me just go back real quick here to temperature, just to talk about temperature conversion just for a second, and significant figures. So when we're doing temperature conversions and sig figs, there's really a general rule, because when we do these sort of conversions, this 1.8 number, sometimes people use 1.8, sometimes people use 1.80, sometimes people use 9/5. So there's a lot of variations that could happen if you're very strict in terms of significant figures when you're doing these things. So there's a general rule that when we do just a temperature conversion, so taking a temperature value to another temperature value in a conversion, we make the converted number look like the original number. So for example, let's go with 41.5 degrees Celsius, and we want to turn that into the temperature in Fahrenheit. We'll hope this works real quick. Temperature in Fahrenheit would then be 1.8 times our temperature in Celsius plus a 32. And if we do that, we will end up with 1.8 times 41.5 plus the 32 gives us 106.7 degrees Fahrenheit. Our original number went to 1 decimal place. We would want to take it to 1 decimal place as well. If our original number was 41 degrees Celsius and we wanted to go to Fahrenheit, again, we would do the exact same calculation, putting 41 in there and 32. And we would end up with 1.8 times 41 plus a 32 gives us 105.8 degrees Fahrenheit. Our original number here, though, is a whole number, which means we would actually round this to a whole number here, and this would be 106 degrees Fahrenheit. So temperature to temperature conversions in terms of significant figures is a little bit different in terms of what you follow. Most people follow this general rule, which is if all you're simply doing is taking a temperature value from one scale to the next, you should make the converted value look just like the original value. If it was a whole number, take it to a whole number. If it went to 1 decimal place, take it to 1 decimal place. You went to 2, take it to 2, and so forth. Question on temperature conversions and sig figs. Okay. All right, so again, when we're doing conversions, you want to make sure you're using dimensional analysis and showing it correctly. Before we kind of move away from conversions, one very common conversions that people really, I'll say it one more time, really screw up is the conversions of the prefixes for our sort of metric numbers and stuff like that. So if you're talking about temperature conversions, Andrew, whatever the number originally was, if you're simply doing temperature to temperature conversions, the answer should look just like the original number. So if it went to 1 decimal place, the answer should go 1 decimal place. If it was a whole number, it should go 1 whole number. In terms of really sort of regular conversion problems, I will say not 100% of the time the number you start with is probably the correct number of significant figures for the answer, but pretty darn close, probably like 97% of the time, that if all you're really doing is just a conversion, maybe several conversions, and you're just doing a conversion problem, again, not 100% of the time will the first number be the right number, but probably most of the time it will be. So just to clarify really the rules, just to make sure everybody's on the same page, when we talk about units and things of that nature, there's really kind of 2 types of unit scales. There really is the metric scale, right? And there's kind of the English scale that we use, and pretty much everybody else uses the metric system. And so there's a bunch of metric to metric conversions, and there's a bunch of English to English conversions. And then there's some that cross over where you go metric to English type conversions. And in science, we kind of use the SI versions of units. The SI version of units is really based off the metric system. That's the international system of units developed in 1960, basically to kind of make everybody use kind of the same type of units in chemistry. But overall, there's these sort of different systems. And when we do a metric to metric type conversion, like, say centimeters to meters, right? Metric to metric. That's considered an exact number, which means you don't have to worry about that conversion factor when you do conversions. When you do an English to English sort of conversion, like maybe do like inches to feet, for example, right? English to English, we don't have to worry about it. It's considered an exact number. When you cross over going from, say, metric to English type units, those are not really considered exact numbers in reality. So, for example, if we did, what would be one? Maybe like 453.6 grams equals a pound, right? Pound is more English, grams are more, kilograms is more metric. This technically would not be considered an exact number, which means if you're using this as a conversion factor, this number would be exact the one, but you would take these 4 significant figures into account. And usually, though, what will happen is that original number, would still probably be the right number. So technically speaking, if we did 32 grams and we wanted to know how many pounds, right? When we do this, it would be 32 grams. We would use that as our conversion factor, 453.6 grams per pound. And when we would do that, we're going to take basically 32 times 1 and divide it by 453.6, gives us a number like 14515.2. Grams would cancel. We would be left with pounds here. And really significant figure wise, we would look at this number, which is 2 significant figures. And really, technically speaking, this number right here would have 4 significant figures. So by default, it actually does still end up being this number. And that a lot of times is the case, which is why I say if you're doing sort of a conversion problem, probably 98% of the time, 97% of the time, if you look at the significant figures in that first number, even if you got like an English to metric type conversion, you'll probably still be okay. And again, there are a few exceptions, obviously, but in most cases, that original number usually has kind of the right number of significant figures. That means technically here we would go to there and we would take this to like 15,000 pounds, no decimal, giving us 2 significant figures. Question on that? I hope that answered your question there. Other questions on that? So the short answer is you're probably in most cases be okay if you just doing conversions, look at the first number and whatever sig figs it has, probably the right answer. But again, just keep in the back of your mind, technically speaking, when you cross over that metric to English, these are not usually considered exact numbers, and you technically should take those into account. The only one that is sort of considered an exact conversion is the one we used earlier. The 1 inch is exactly 2.54 centimeters. So this is like the only sort of, or one of the only sort of metric to English conversions that is still considered an exact number. But most of the other ones really are not. Any questions on that there? Okay, so what I was saying as well in turn before we move on from this conversions is, the thing that most people really screw up on a lot is when we use those prefixes, right? So since these things are based off of the metric system, we have a lot of prefixes that we sometimes use. So for example, we have milli, for example, which is 10 to the minus 3. We have, say, kilo, which is 10 to the 3. We have mega, which is 10 to the 6, for example. We have nano that we've used, which is 10 to the minus 9. So when people see these sort of prefixes on the table, it is very common that people use these incorrectly or backwards. So for example, if I want to do milliliters and liters, this liters is the base unit, right? This is the prefix unit. And when we look at this number for milli, that is how much there is in the base unit to one of the prefix units. So 1 milliliter would be 10 to the minus 3 liters. And that is the right way to do that. Just like if you had 1 milligram, there is 10 to the minus 3 grams, grams being the base unit. Just like if I had mega here, 1 megaliter is 10 to the 6 liters in this particular case. If I had 1 nanometer like we did, that is 10 to the minus 9 meters. Super common. People always will get these guys reversed, and they'll go 10 to the minus 9 nanometers is 1 meter. So again, keep that in mind, that when you see that sort of prefix, what that is telling you is in one of the prefix units, that is how much there is in the base unit. So in this case, nanometers and meters. Meters is the base unit. One prefix unit, 10 to the minus 9 base units. Question on that there. Okay. All right, any questions on, let's see here, prefixes, conversions, dimensional analysis, any of those things? Okay, let's see here. So usually some of that basic stuff at the beginning. Yeah, so that's what this represents, by the way. So when we say something like 10 to the minus 3, that's the same as 1 times 10 to the minus 3, if that's your question. So it's the same thing. Just like when we say 10 to the 6 would be 1 times 10 to the 6th, if that's your question you're asking. So that would be kind of the same thing here. 1 milliliter would basically equal 1 times 10 to the minus 3 liters. And that also is a good point as well. If you need to punch something like this into your calculator, by the way, going back to our sort of exponent buttons, if you will, depending on which buttons you sort of have, that's maybe the safe way to do it would be to punch in, 1 exponent button. Again, we talked about make sure you use your negative button and say 3, and that would give you 1e minus 3, which is 1 times 10 to the minus 3, which would be the same as this guy when you punch it into your calculator. Personally, on my calculator, since I have this button, I actually could just hit the button and minus 3 or negative 3, and I don't need to put the 1, but you can put the 1. So sometimes it comes okay. So that's how you would punch it in as well. So all these on these typical tables, when you see this number, it's basically 1 times that sort of number. And again, that's a good way to kind of put it into your calculator as well. Other questions on that? Okay, so we talked about that. So then let's talk a little bit about density. Density is the relationship between mass to volume. So density is mass divided by volume. And this is sort of like an equation here that we can rearrange. If you rearrange and solve for volume, volume would be mass divided by density. And if we wanted mass, it would be volume times density. Sometimes people remember everybody's favorite place, the DMV. Yes. Density is mass divided by volume. Volume is mass divided by density. Mass is density times volume. So sometimes people remember the good old DMV triangle there. Common units of density. Grams per milliliter are grams per cubic centimeter. Remember that a milliliter is the same thing as a cubic centimeter. And a cubic centimeter is the same thing as a cc, which stands for cubic centimeters. Like in those medical shows, when they say give the guy 5 cc's of something, they're saying give the guy 5 milliliters of something. So that is basically the same thing. Remember that when we talk about, this is typically the units that we see for solids and liquids. For gases, typically the units are grams per liter. So we'll see that a little bit later on in the semester when we talk about gases. But actually the density of gases is actually grams per liter. But most of the time we deal with these guys. And again, there's a few different ways we can get the volume. We obviously can just simply take a volume reading, right? So we could read the volume. And that usually would be in milliliters. How would we get something that's a cubic centimeters? Well, if you had like a cube and you took a length times a width times a height measurement, and they were each in centimeters, when you multiply centimeters times centimeters times centimeters, you end up with cubic centimeters, which is a volume. So typically when you cube a length measurement, cubic centimeters, decimeters cubed, millimeters cubed, whatever it may be, it goes from a length measurement into a volume measurement. So that's, again, a common way to get maybe the volume of a solid by taking a ruler out, measuring a sort of square solid, if you will, or a cube. Another very common way that we get volume, especially when we're dealing with density, is what is sometimes referred to as volume by displacement. And basically what that means is if you start with, say, a solution of water or something like that, and you take a solid guy and you throw it in there to go for a swim, what's going to happen is, with the solid in there, the volume level of that liquid will rise. And basically the solid will displace a volume that's equal to its own volume. So if we take our initial volume and our final volume, that's basically the volume of the object we jumped in there. So the volume of the object is usually the final volume minus the initial volume in that particular case. And that's a very common way, that we can calculate the density of an object. And a very simple way to figure out the density of object is to throw it in there. When we talk about sort of throwing things into water, for example, if something is less dense than liquid water, it will float. If something is more dense than liquid water, it will sink. Water itself is kind of unique. Actually, ice is less dense than liquid water, which is very unusual sort of property. Most of the time, things in their solid state are more dense because they're packed in very tight to each other. The reason ice doesn't do that is because when all those water molecules come together in the solid form or ice form, they actually hook up with each other in such a fashion that it creates these big old pockets of empty space between them. And if you think about what density is, it's mass divided by volume. By having all that empty space, it's making the volume much larger, which by default makes the density smaller in this particular case. So that's sort of an unusual property of water. That's why when we put ice in our drinks, the ice floats to the top, right? And it's because there's actually a lot of that empty space between how those water molecules come together, making it much less dense, and again, will float, which is, again, a very unusual sort of property. So for example, if we had a piece of metal that had a mass of 32.55 grams, and we put it into 25.0 milliliters of water, and it rose to 27.5 milliliters of water. What is the density? Well, in our example here, my initial volume is 25. My final volume here would be 27.5 milliliters. So to find the volume of the metal, we would take our final volume, which is 27.5 milliliters, minus 25 milliliters, which means I end up with 2.5 milliliters when I do that subtraction. I have the mass given to me already, which means my density would be my mass divided by volume, which would be 32.55 grams divided by 2.5 milliliters. 32.55 divided by 2.5 gives us a number of 13.02. The units here do not cancel, so it's grams per milliliter. The number stays with the grams part. It's always 1 milliliter. The reason I did this one, first off, any question on the actual calculation here before we talk about sig figs? The reason I did this one is it's a good demonstration of sort of keeping track of things when we do significant figures. The first step that we did here was subtraction, which means we subtracted 1 decimal place from 1 decimal place, which means our answer should have 1 decimal place. But although it has 1 decimal place, when I take this number down here and use it, it has 2 significant figures. And basically the last math that I'm doing is 4 significant figures up on top divided by 2 significant figures on the bottom. So since I'm dividing, I want to look at sig figs, which means really my answer should end up at 2 significant figures in here, really based off of the volume subtraction I did earlier. And it really should be 13 grams per milliliter. Any questions on that there? All right. Any questions on any of that stuff that we talked about here? I think that covers most of all that introductory stuff. So again, as I mentioned before, you are responsible for the stuff in your book. Again, you can find it in that introductory chapter, but you do need to obviously give things to the proper number of significant figures. You need to show your work using dimensional analysis and showing the units and conversion factors that cancel and stuff like that. You need to know obviously about density, scientific notation, and all that kind of stuff. Temperature conversions. Any questions on any of that stuff here? All right, so let's talk a little bit about the study